All right, let's do some solving. So we talked in our section on inverses a lot about the square root as a analogy to solving other or manipulating other kinds of inverses, and it's going to be we're going to have a similar issue with solving. So we talked about the idea of being careful with things like square roots. If somebody asked you what's the square root of 25, it's very important that square root is a function. Functions mean one input gives you one output. So the square root of 25 is only allowed one answer. It is 5. Now, a lot of people try to say plus or minus 5 because you're so used to solving, but that plus or minus doesn't come from the square root in that way. What happens is, if we're trying to solve something that breaks down eventually to x squared equals 25, and we square root both sides, according to what I've been saying, that square root of 25 had better become 5, and it does. The issue is with the square root of x squared. And you might want the square root of x squared to equal x, but it doesn't. It only equals x if we're within the proper restriction for the square root. So if we know x to be positive, or 0, then the square root of x squared can be x, fine. But we saw an example last time with the square root of negative 5 squared. That doesn't become negative 5, that becomes positive 5. So if x was negative 5, the square root of x squared wouldn't give us back the negative 5, it would give us the positive 5. So the square root of x squared isn't x, it's technically the absolute value of x. And the solution set to the absolute value of x being 5 is that x has to be plus or minus 5. So that plus or minus is not coming from the square root of 25. It's coming from this absolute value that's happening from us undoing a restricted function. The square root inverse being restricted to only part of the domain. And you might not have seen that before. Oftentimes we skip that step completely. Nobody writes that out. Well, I do sometimes, but not a lot. But that's where that plus or minus is coming from. Similarly, when we try to solve something like the sine theta equals 1/2 over here, we are going to use the idea of, okay, we're taking the sine inverse of both sides of this thing. But we have to be careful. Nowhere in this problem are we told that theta lives only within our restriction. That theta is a general angle theta. It can be anything. Again, we're trying to find a general solution. So we have to respect that fact. So even though the sine inverse of 1/2 is going to give us pi over 6 and only pi over 6, we can't say that the sine inverse of the sine of theta is just equal to theta, because we don't know that to be true, because theta is not necessarily within our restriction from negative pi over 2 to pi over 2 that allows that to be true. Now, we don't have some nice symbology like we did for the absolute value. What we have to do instead is immediately break this out into all possible angles that would have created that 1/2. So as soon as we go from here to here, we have to break this into multiple cases, and that's what this is talking about up here. When we have functions that we're using the inverse as a solving technique that have a period of 2 pi, like sine and cosine, we have solutions in this larger form. Now, I really think this should say x1 equals theta plus 2 pi k, and x2 equals theta 1 equals theta 2 plus 2 pi k, because we're often going to have two sets. And let's look at the reason why that is. So this is asking, what angle makes sine output a 1/2, and we know that happens at pi over 6, and that is the only place it happens within our restriction. So that's why the sine inverse can only tell us the pi over 6. But we know that this angle could have been outside of that restriction, so we have to essentially rebuild the other possible answers it could be. What other answers outside of our restriction could it have been? Well, we know the sine can also give us a positive 1/2 over in quadrant 2. Quadrant 2 is outside of the restriction, so the inverse wouldn't have told us about it. We have to create it. Now the nice thing is, we know that these two angles have the same reference angle, so this is still pi over 6. If they're both giving us a 1/2, they have to have the same reference angle. So this had better be 5, not 7, 5 pi over 6. So we know that 5 pi over 6 is also a possible answer for this problem. So we have two possible answers here, one in quadrant 1 and one in quadrant 2. In quadrant 3 and quadrant 4, the ratio would have been negative, so there can't be any in those quadrants. However, we also know that anything coterminal to that pi over 6 is also going to make this thing equal 1/2. And anything coterminal to the 5 pi over 6 is also going to make the sine equal to 1/2. And that's why we get this form, that plus 2 pi k. We get pi over 6 and anything coterminal to it. Remember, if we add a rotation, we're going to get another angle that's coterminal. And we can add that rotation any number of times we want. That k, an integer in both cases, that k is just how many extra rotations you want to consider. So pi over 6 plus anything coterminal to it, any whole number of rotations, or negative number of rotations. I really do want you to think of this as and everything coterminal, because that's really what that's saying. But also for 5 pi over 6, we also get 5 pi over 6 and anything coterminal to it. And I'm going to say 4k and integer. If you want some fancy symbology for it, k element of the integers, if you want some fancy symbology. But for k as an integer, it's fine. So we can't, it has to be an integer because we can't add half rotations or third rotations because we'd be somewhere else. So it's plus full rotations, and if k is negative, it's minus full rotations. But this gets you a set of solutions that gives you every possible value for theta that makes that statement true. And that's what solution means. A solution is a value for the variable or variables that make the statement true. So even though the sine inverse can only give us one of those values, we have to use our solving techniques to create not only the other answer in the first rotation, but also every other possible coterminal. And I really do want you to think of this as kind of being the same thing as when you solve something like x squared equals 16 and you square root both sides, even though the square root of 16 is only 4, our solving technique reminds us we have to put that plus or minus in. And we know that that's because square roots have issues with minuses, even if we might not remember this whole absolute value argument. But we know square roots are restricted, so when we solve, we have to undo that restriction. It's the same thing over here. When we solve, we get only the answer within our restrictions, and then we have to go out and create the other solution within one rotation and all the coterminals. So it's adding a lot more than just plus or minus, but it's the same idea. It's undoing the natural restriction of our inverse function. And it might seem either weird or counterintuitive, or even might seem rude. We just had all that conversation about putting in that restriction, and now we're talking about undoing that restriction. Well, you can imagine if you walked up to your calculator. I don't know why your calculator is so big you're walking up to it. But if you grabbed your calculator and typed in sine inverse of 1/2, and it said there are a billion solutions to that, and here are all of them, you're not going to like that, and the calculator can't do that. But what we can do is build a function, which again means one answer, for the sine inverse within a restriction, and then when we need to undo that restriction, we understand how to do that and perform that. Again, similar to how we handle even indexed radicals, like square roots. So that's the general idea. It'll be a little bit different when we talk about tangent, because tangent has a smaller period. It's actually a little bit nicer in some ways, but we'll get there. So just like we talked about yesterday, and just like we would with square roots, the first thing we want to do in solving any trigonometric expression is isolate the trig function. So move everything out of the way, so all we have is that trig function equaling something. So find all real numbers that satisfy that, so find all solutions to this. Step 1 is to isolate the trig function. That was already done up here. So divide both sides by -2, and then get the sine of alpha equals what will be -3. And frankly, as soon as that happens, we say, done. There are no solutions. And we know that because we know sine only outputs values between -1 and +1. There is no angle for which the sine of that angle is equal to -3. So technically we're done. Now we could think about saying, okay, let's try to take the sine of the sine, or sine inverse of the sine of alpha, and have that equal the sine inverse of -3. But as we talked about yesterday, that's not defined, so that can't exist, so there can't be any solutions to this, so done. No solutions. And it's similar, again, I'm going to use square root as an example. If you say -2x squared equaled 6, and you divided both sides by -2 and got x squared equals -3, you'd stop and go, well, nothing squared is negative, as long as we're in the real number system. So x squared -3, that could never happen. So you'd say no solutions. Same thing here. This is outside of the possibilities for sine, not because it's negative, but because it's outside of the range from -1 to +1 that sine has to live in. So again, similar to our x squareds and square root arguments, but just, more dramatic. Now here we have to be a little careful. We have this 2 in here. Now, after having done our double angle formulas, you might think, hey, let's throw double angle formulas at that, but we actually don't want to do that. We want an isolated trig function, and we have here an isolated trig function, so we want to work from there. So we're going to do the same thing. Do the sine inverse and the sine inverse. Sine inverse of 1/2, we already know, is pi over 6. But just like the problem before, it's pi over 6 and anything coterminal. But also, just like the last problem, it's also 5 pi over 6 and anything coterminal. Again, if you look at your unit circle, because both pi over 6 within the restriction and 5 pi over 6 outside of the restriction, both of those have a sign value of 1/2. And anything coterminal will also work. So we get, those two sets of solutions, just like we did on the other one over here. However, over here we had, the sine inverse of the sine of theta, so theta equaled that. But here that 2 theta remains behind when we get rid of that sine function. So there's a 2 theta left behind here. Now be very careful. That 2 theta has to appear as soon as you do this sine inverse thing. As soon as you do that, all of these extra solutions exist immediately. We can't do any of the, if you want to solve for theta here, you think divide off that 2, divide off that 2. And that's absolutely true. But we have to get the full general solutions first. We have to do that expansion of all possible rotations before we start doing any other manipulation, or things are going to go wrong. And again, just like square roots with the plus or minus, as soon as you square root both sides, if we had x plus 1 squared equals, 6, I don't want 6, 9, make it nice. As soon as we square root both sides, we have to put that plus or minus 3 in there, and then subtract the 1, so that plus or minus stays in the right place. If we'd have left it just the 3 and subtracted the 1, got a 2, and said, it's plus or minus 2, that would be wrong. It wouldn't work. So, similarly, here we have to get both general solutions, or both full solutions first. Then we can divide both sides by 2 here, and get theta equaling pi over 6 divided by 2 is pi over 12, plus 2 pi k divided by 2 is just pi k. And down here, divide everything by 2, and we'll get a nice 5 pi over 12 plus pi k. Do be careful, that 2 does have to divide into both pieces there. It is distributing through. So that gets us our general solution. Do be very careful about that. I know I've stressed it, but make sure you open up to all the solutions before you start doing any manipulation there. So, down here, find all zeros for the function. Well, that sounds like we're doing something a little more dramatic or weirder. But remember, the zeros of a function are just where is that function equal to 0. And, we could graph this function if we wanted to. We know it would look like tangent does, but it would have be more stretched out. It would have a, different period. It would even have a nice big phase shift over it. But, whatever that graph looks like, we know it's going to equal 0 many, many times. It'll be shifted, and not shifted that way, actually, and compressed and everything. But we know it's going to have multiple solutions, so we have to make sure we respect that and give all the possible solutions this thing could have. And we're going to do the same thing we did before. isolate the trig function, so that's this whole thing. So I'm going to divide both sides by 3. That's the nice thing about finding zeros. If you divide off, it's just going to be 0. And then we need that tan inverse. So we're going to get the 2x plus pi. That's going to stay there because we're essentially taking the tan inverse of both sides here. And where is the tangent 0? Well, we know the tangent is 0 at 0 because the y value is 0. That's the answer within our restriction from negative pi over 2 to pi over 2. But also, it's 0 over here at pi. So we get one solution, just like we did for sine, one solution within our restriction, and one solution that's still in the first rotation, but is outside of our restriction. So that 2x plus pi could equal 0 plus anything coterminal. I don't know why I put the k first. Or the 2x plus pi can equal pi plus anything coterminal. But wait, your instructions said if it has a period of pi, we don't need a 2 pi k, we just need a pi k. And the reason for that is, notice these two solutions are exactly pi radians apart. And that would have happened no matter what. If we were supposed to get 1 over the square root of 3, then you'd have that solution up there, and you'd have a solution up here at pi over 6, and you'd have a solution down here at 7 pi over 6, because tangent is positive in those two quadrants, and they'd be exactly pi apart. So the nice thing about tangent is we don't need two pieces. We can always get away with tangent of just doing one piece and adding pi k instead, because tangent has that natural reduced period. So tangents tend to be nice. We just got to be a little careful. And then we can finish solving for x the way we normally would. So, subtract pi, give myself some more space. Yeah. Smaller. There we go. So then 2x equals negative pi plus pi k, divide by 2, divide by 2, then x equals negative pi over 2 plus pi over 2k. And that would be a fine general solution. I might, tend to make note that your answer is pi over 2 and plus any number of pi over 2's. So like if k was equal to 1, this would be negative pi over 2 plus 1 pi over 2 would be 0 again. So 0 being a solution, we could really just put pi over 2k here, and then that negative 1/2 is just the solution when k is negative 1. But, really, that's a fine answer. You could leave it there. But if you want to be clever, you could simplify it down to that. So solving tangents are nice. They're a little bit smaller. You don't have to deal with quite so many other solutions. How are we doing on time? Oh, pretty good. Okay. So finding particular solutions. You do have to be a little careful about this. You have to be careful when solving. You always do. So when solving within a domain restriction, you don't need to list all solutions. That's true. Only the ones within the given domain, so only the ones within a given interval. But it's very important to find that full general solution first. Anything that changes your period or a phase shift, So anything going on inside that function can move your solutions around, generate extra solutions within your interval. So if you don't create the full general solution first, you will miss or lose or mistakenly put solutions to your problem. So make sure you always find your full general solution first, and then evaluate it at different values for k to find things that live within your specified domain. So in this particular case, because there is no phase shift and there is no compression factor in there, that's not, sine of 3 theta plus pi over 6 or something like that. We know our natural solutions that we get are going to live within our natural, our natural 0 to 2 pi. But we'll see later with problems. If you start having things going on in there, things are going to go south really fast if you're not careful. So anyway, we solve it the same way we did with the last ones. We solve by isolating the trig function. So that would be sine theta equals -1. We know sine is -1. Where is sine equal to -1? Sine's equal to -1 down at -pi over 2. So we're going to get one solution at -pi over 2 and anything coterminal. And usually there's a second set, but anytime it's quadrennial, remember when it's on your axes, you actually only get one. You can imagine if there was one over here, then there would have to be one over here for this negative value and that negative value on the other side. But when it's on the actual axes, you only get one solution instead of, essentially you can imagine those two solutions coming together. So, that's a nice case where we only get one set over still 2 pi, because anything coterminal to this is also going to give us a -1. But it's nice that we don't have to deal with that second set again. And then we would just check values for k. Remember, k is an integer. Find values for k that put our answers within this restriction. Now, what do I mean by that? So pick values for k. If k equals 0, we get -pi over 2 plus 2 pi times 0. So that would just be -pi over 2. Now, is -pi over 2 in this interval from 0 to 2 pi? No. So that's not a solution. What about k equals 1? Well, if k equals 1, we'd get -pi over 2 plus 2 pi times 1, which is -pi over 2 plus, get some common denominators, 4 pi over 2. It's the same as 2 pi. So we get, -pi plus 4 pi is 3 pi over 2. So when k equals 1, our solution is 3 pi over 2. And of course that's coterminal to -pi over 2. That's the point. Now, is 3 pi over 2 within this restriction between 0 and 2 pi? Well, yes it is. So boom, that's a solution. What if k is equal to 2? Well, if k is equal to 2, we'd have -pi over 2 plus 2 pi times 2. So -pi over 2 plus 4 pi, which would be -pi over 2 plus 8 pi over 2 to get common denominators. So when you add those together, we get 7 pi over 2. And 7 pi over 2 is bigger than 2 pi. Okay, so 7 pi over 2 would be outside of our restriction and too big, so neither of those made a solution. So cool, we get one solution. That's our answer. Theta equals 3 pi over 2. And we just keep trying values for k until we find every possibility that gives us a solution within that restriction. Let's go down here. Ooh, that's fun. A secant. Well, we certainly know that dealing with secants can make things more complicated. And you might say, well, I don't want to deal with a secant. Okay, if you don't want to deal with a secant, don't deal with a secant. We know secant is 1 over cosine alpha. And then if we wanted to, I don't like having that in the denominator, so I'm going to multiply both sides by cosine alpha. Cosine alpha. So we'll get 1 equals the square root of 3 cosine alpha. Then divide both sides by the square root of 3. Divide this side by the square root of 3. Now we get 1 over the square root of 3 equals cosine alpha. So we've changed this secant problem into a cosine problem that we can solve. Great. And we didn't necessarily have to go through all this work. We know secant and cosines are reciprocals, so if we want to change the secant to a cosine, that square root of 3 became 1 over the square root of 3. It's reciprocal, so that should seem fairly natural, but if we want to do it formally, we certainly can. And, looking at that, you might go, well, do we want to rationalize that? We certainly can if we want to, and turn that into the square root of 3 over 3. Whether that's valuable or not when we're about to find what the cosine inverse of 1 over the square root of 3 is debatable, but either way. Now it kind of looks like, 1 over the square root of 3, that would be a nice tan inverse of one of our standard angles, and we see a lot of square root of 3 over 2s for our standard angles for cosine. But that's not a standard angle for cosine. So if we are in a situation where we have something that's not one of our standard angles, then we have to go to technology. So you'll notice if you get a scientific calculator or your, Desmos eTools, if we grab one of those and say, hey, what is the cosine inverse of 1 over the square root of 3, and you can rationalize it or not when you put it into the calculator or computer, it's going to spit out a single answer, and that single answer, let me find out what it is, 0.9553. 0.9553. We're going to have to deal with it as a decimal approximation because that's all we have, because again, it's not one of our standard angles. So 0.9553, so a little less than 1, so probably 52, 53, 54 some odd degrees. But remember, it's also anything coterminal to that. And additionally, we have to think about, do we get any answers in other quadrants? So that's about 1 radian, so 1 radian's about up there. So 0.9553 radians. Remember, pi over 2 is here, so that's 1.57, so 0.9 radians is about there. And the cosine of that 0.9 radians is apparently 1 over the square root of 3. That's the whole point of finding the inverse. But clearly there's going to be another angle down here in quadrant 4 that's also going to have a cosine value. That's the positive, because again cosine's positive in quadrant 4. That's also going to give us a 1 over the square root of 3. And we need to figure out what that angle is, because that will form our second set of solutions. And we can do that in one of 2 ways. One, we can say, well, we know it has to have the same reference angle as the first one. So we could simply say it's negative 0.9553. That would be easy. Only works for cosine, by the way. But since we know we want solutions in between 0 and 2 pi, it might be nice for us to just kind of automatically go, hey, what's this angle? And we know that angle better be 2 pi minus this reference angle of 0.9553. So minus 0.9553. And I don't know what that is, I gotta ask. 2 pi minus 0.9553 gets us about 5.328. So, where was that? Okay. 5.328-ish. So 5.328 plus anything coterminal. So that would give us our general solution. But we were only asked to give solutions between 0 and 2 pi. Well, that means the 0.9553 is a solution, because that's between 0 and 6.28. Remember, 2 pi is 2 times 3.14. The 5.328 is going to be a solution. And it should be clear that if we take this positive value and add 2 pi, we're going to be past one rotation. And if we take 5 and change and add 2 pi, we're also going to be outside one rotation. You go, anything coterminal to these is going to be outside of the first rotation. So first rotation between 0 and 2 pi. So we only get those two solutions. Now again, you might be thinking, well, why do we have to care about this if they don't matter? The only reason they don't matter is, again, there was no compression factor and no phase shift. When we do this one down here that has both a compression factor and a phase shift, we're going to have to care about those other k's a lot more. Okay, I think I'm going to cut this video off before we do the using identities, just to keep it shorter. So we'll make this one the last one for that video. Solving takes a lot of practice. Make sure you put the time in to get all of that practice. It can be a little strange, as you can probably see. So do get that practice. Put the time in. It'll pay off. Okay. Normally, step 1 would be isolate the trig function, but this one's already isolated, so that's good. So we can go right to thinking about that cosine inverse. That is going to leave us with theta over 2 plus pi equal to the cosine inverse of negative 3 pi over 2. And again, you can always draw your diagrams out. Cosine being negative means we have to be up in quadrant 2, because the inverse is only defined between 0 and pi, and cosine is negative over to the left where the x values are negative. And if we check on what angle that is, we'll get an angle of 5 pi over 6. So 5 pi over 6 it's often called our principal solution. That's the solution within cosine inverse's natural restrictions. So it's the principal solution. But we also know we're going to get another set of solutions outside of this restriction, because it's not quadrennial, it's not on one of our axes. And that other restriction is going to be in the other quadrant in which cosine's ratio is negative. So that's going to be down here at some other angle that gives us negative square root of 3 over 2 for cosine. And it should be fairly clear that this, these angles have to essentially be the same. So we could say negative 5 pi over 6. Again, that only works for cosine. Also, you could make arguments like, hey, this reference angle has to equal this reference angle. Okay. That reference angle is pi over 6, so that reference angle has to be pi over 6, which would make this whole thing 7 pi over 6. Okay, so if you don't want to use the negative value, don't use the negative value. Use the 7 pi over 6. Whichever one you want. Doesn't matter. We just need an anchor. Because then we're going to say plus anything coterminal. Even though we only want answers within this restriction, we need to care about those coterminals, especially now that we have an actual compression factor and phase shift. Now that's not our general solution yet. We still have to solve for theta. So I'm going to subtract pi. Now I'm going to be careful here. I know it's weird to work sideways. Maybe I should put those, orient those differently in the future. We'll see. So theta over 2 equals 5 pi over 6 minus pi plus 2 pi k. So to subtract those, I need common denominators. I'll give myself some common denominators. So theta over 2 equals negative pi over 6 plus 2 pi k. And then multiply by 2, and we get theta equals, distribute that 2, so negative pi over 3 plus 4 pi k. So that's one set of solutions for our general solution. And over here we have to do the same thing. So subtract pi. In common denominators, that'll be 6 pi over 6. So theta over 2 equals 7 pi over 6 minus 6 pi over 6 is 1 pi over 6 plus 2 pi k. I don't like that that's so thick. Then multiply both sides by 2. And we'll get theta equals pi over 3 plus 4 pi k when we distribute that 2 through. So that's our other general solutions, or set of general solutions. So if we were just asked for the general solution, it would be those two pieces, but we were asked for the solutions within a given interval. So again, we still want to find the general solution first, but then we'll try values for k and see what we get in our different intervals, or from our different sets. So if k is equal to 0 here, I'm going to call this theta 1 and theta 2 for our two different sets. Then theta 1 would be 4 pi times 0 with 0, so we would just get negative pi over 3. And theta 2 would be, again, 4 times pi times 0 with 0 plus pi over 3, pi over 3. And that would actually be a solution because it's within our restriction. Great. If k was equal to 1, then negative pi over 3 plus 4 pi times 1, that's going to be way big. Negative pi over 3 plus 4 pi. Get common denominators, would be 12 pi over 3 would be, what, 11 pi over 3? That's way bigger than just the first rotation. So I can write 11 pi over 3, but it's not going to be a useful solution. And it should be clear that if we let k equal 1, pi over 3 plus 4 pi, it's going to be bigger than 2 pi. Heck, it's going to be bigger than 4 pi. So notice that compression factor pushed a lot of solutions way too far out. So I'm just going to say too big here because it's not going to give us any solutions. Do be careful. We always want to consider negative values for k, but this is already negative, so if we let k be -1, we get negative pi over 3 plus 4 pi times -1, which, just to be formal, 4 pi over 3 minus 4 pi, which is going to be some big negative number, so that's going to be too small. And if you let the k over here be negative, you're still going to get pi over 3 minus 4 pi, because k -1 times 4 pi is -4 pi. And that's still going to be a very negative number, so it's still going to be too small. So generally you want to do it this way. Put in your k's until you get stuff that's too big, and negative values. Check those negative values, make sure you get things that are also out. That means that pi over 3 is our only solution to this thing. So the only solution to this thing is theta equals, pi over 3. So you do have to be careful about those restrictions. Do make sure you find your full general solution before you start trying to decide what is in your interval and outside of your interval, because you can make mistakes with that really easily. The hardest part about this tends to be for people, and different people struggle with different things, of course, but getting the first solution that comes from your inverse function, generally we can do. Finding this second solution is generally the hard part when you're working with sine and cosine, because you have to do them differently because the quadrants are in different places. So I always recommend draw out the diagram. You'll see I did that up here with this one too. Pi over 6 was our one solution, and we know sine is also positive up in this quadrant, so that gave us a separate solution up there to get the two solutions that we had to care about. So that is usually the hard part. That takes some practice. Get that practice, put the time in, and make sure you are drawing those diagrams. It will help. So there is more to this section, using identities to help with our solving, and then handling things that are like quadratics. So it'll kind of combine your skill with solving quadratic equations with this trig solving. It doesn't really add a lot to the trig solving, but it does make for long problems because you have to do all of your quadratic solving techniques and then all of your trig solving techniques. Using identities is just going to be using things like our Pythagorean identities and our double angle formula type things, if they're handy, to make all our arguments match, and ideally to simplify the problems before we use our solving techniques. So I'll make a separate video about that just so it doesn't get to be too long and my video card doesn't start to balk at me. So keep an eye out for that. And as always, have a wonderful day.